So here's our last optimization algorithm, but this time it's for the find function. And this is using what's called path compression. So again, as you know, the longer it takes for us to find something, because it has to go from the bottom, as I'll call it, it doesn't have to be the bottom, but it has to go all the way up to the root. And the more and more nodes we have, the more and more that's going to be a problem. We're trying to shorten this. So what's going to happen is that this algorithm is literally and figuratively going to shrink the tree by updating the element values of each of them directly to the root. So that eliminates a really long line to now basically you're directly connected to the root. So it's really going to shrink that tree and make it, well, into a shrub, basically. But anyway, but it's done while you're finding the value. So here's the key ingredient. If you have a massive tree, but you only do a find on a couple of nodes, some of those values that it went through will go ahead and then be readjusted and connected directly to the root. Some of the other ones are still going to dangle out there. So notice this is a relatively interesting setup for this because we may not find or do a find on every single node. So there's still going to be some that might be dangling out there. So just a heads up on that. For example, in this one right here, when we do the path compression, it's going to use recursion. And the base case is until you find the root, you're going to return the root value and it's going to reassign the value to each and every node that it went through to get there at the very, very end when the stack collapses. So in this example that we have here, is that here was the before picture, and this is after we do a find on the values 2, 4, and 5. So it'll go to 2, it'll still move up because this is the original tree, and then it'll finally get to 0 and say, oh, wait a minute, I'm finally at the root. So let me update 1. You're going to point at 0, which it's already doing. And then as it collapses, we'll still go down to 2. And it says 2, you go ahead and start pointing to 0. And the same thing that we have right here. Same thing with 4. Same idea for all of them. Is that it's still, I want you to picture this as being 3 deep. Then 3 deep, 1 would still be pointing to 0. The next value would be pointing. So notice it's going to start pushing things up to have it directly connect with the root as we had here. So why did 6 remain the same here on this one? Well, very simple. We didn't do a find on 6. If we did a find on 6, then yes, we would go ahead and make it a little bit more compressed. But we didn't do one, so it's not going to do it. Whereas 5, why did 5 remain the same? Because it was already connected to a root. You can't get any closer than that unless you're in it. So that's why those two values in this tree over here did not change any at all. So, a couple other examples for you here real quick. So first of all, here's our disjointed set without using path compression. And then here's our disjointed set after we did a find on 15. So again, this is how it originally was. Did a find on 15, went through 14, and then to 1. So 15 would collapse in and do some compression, obviously, and then now it has directly linked to 1. And then we have the same idea for over here for our other set of path compression as well. So by the power of video editing, I changed this last exercise right here, or example, I should say. It's not really an exercise. In the path that we have here, you'll notice we have a nice long tree. I shouldn't say nice and long because that's bad news, especially for the find. But after the compression, and specifically watch which I'm finding for, I'm looking for find of 0. So think of it this way. We start from 0, and we link up to 1, then to 2, and then you figure out how this goes. But again, each time we're going through this, we're storing and we're waiting for the rest of the call stack to be done because it's done recursively. Once we reach 4, the stack starts to collapse. Say, wait a minute, okay, 3, you're now pointing directly to 4, which is already happening. Then we have 2, 4 was the answer. You're now to be directly connected to the root. 1, your root was originally 4. Now I want you to directly connect to 4. And then the same thing, obviously, with 0. So notice path compression can make a major difference when it comes to longer items that happen to be not being given much attention here, and then obviously go ahead and compressing them quite readily. So I wanted to show you something that was more than just 2 layers or 3 layers of a tree, and how impactful that fine, especially at a lower level node, can really change the path and the overall depth of a tree. So the other part I wanted to show you was a very simple recursive function for this. So this is the fine. You can tell it's recursive because here's the other fine right here. You know, if it's less than 0, we know it's got to be a negative number. And that means, well, it's a root. And we found our root. We're going to return that index of the root. And that's where the rest of this is done. And notice the very end here with that return of the assignment here of f of x, sorry, right here, s is x. That's how we then go ahead and update now how all of these are now updated to 4 because the stack is finally collapsing and we get a response. So that is the overall code for our path compression in disjointed sets.